field. Okay, got it. Significantly stronger emission lines, and also that you can see here in the plot on the left. They were characterized by higher specific star formation rates, and also were much more compact and with low stellar mass. So these are the characteristics that we have to look for in low redshift galaxies to find for analogues. Another piece of this introduction that I wanted to talk about is the importance of the rest frame UV spectra. So UV spectra provide a unique window on many processes, mass star population, chemical evolution, feedback processes, and the study of reionization, because UV diagnostics can characterize the stellar and nebular evolution across all redshift. Indeed, in the local universe, we have JWST data that can allow us to study UV spectra. Then moving towards intermediate redshift, we have the rest frame ground-based observatories that we can use. And then moving at even higher redshift, at redshift higher than 6, we have the rest frame infrared. And of course, in the JWST era, we will have more and more observations at redshift higher than 6 and also higher than 10, where we will have only UV spectra available. And these are just two examples of two high redshift galaxies where you can see the Lyman alpha feature, the carbon 3, carbon 4, oxygen 3, that are some of the emission lines that are visible in these systems. But in order to use these lines to understand the properties of the interstellar medium, we have to calibrate them before. So to do this, we need a framework of local galaxies that are redshift analogues, as I was saying before. And to do this, Class C is the best survey, because Class C stands for Cost Legacy Archive Spectroscopic Survey. It's a survey that collects both archival observations of JWST and new observations, covering from the Lyman alpha to the carbon 3, so from 1200 till 2000 angstrom. The PI is Daniel Berg, and it's characterized by 45 local systems that are also characterized by properties highly representative of the redshift universe. For example, in the plot that you can see on the left here, you see the stellar masses go between 10 to the 6 and 10 to the 10, but with respect to the local universe that is shown by the turquoise line or the dashed line, the classic galaxies that are the purple dots are characterized by much higher star formation rates. They are characterized by higher specific star formation rates, and are also characterized by very high 302 line ratios and higher densities. And these are all information that you can find in the classic presentation paper that was recently accepted in APJ. This is one of the spectrum that we have for one of the galaxies, where you can see the coverage from the Lyman alpha till the carbon 3. So the important thing of Class is that it collects together 3 COS gratings. COS is the instrument on JWST. Before Class C, only 2 galaxies had in the JWST archive had the coverage, at the complete coverage that you can see here now. And also Class C has a very high spectral resolution with respect to previous data. So it allows us to do synergistic for UV science on many points of view. Specifically, what I've been doing is the study of the ISM properties, as I was saying before, with the UV emission lines. The UV emission lines that we investigated are shown here with highlighted how many galaxies are characterized by these emission lines with signal to noise higher than 3. And the important thing is that and this is an example for one of the galaxies of some of the emission lines fitted. The important thing is that for all the galaxies, we also have optical spectra, and we know much better how optical diagnostics work. So doing a comparison, we can learn more about UV diagnostics, see how they compare with optical diagnostics, and see if we can provide a UV-based toolkit for the community in order to interpret the JWST data that we will have in the future. So final part of this introduction, this is star forming regions. You can see bright, very young stars, massive stars that emit UV light, and with the UV radiation and the strong stellar winds, they are basically created this hole in the image. And what you can see is that here this image has 3 colors because you have a different kind of emission characterized by different emission lines, because star forming regions are stratified. In this much complex cartoon that I took from Berg 2021, what you can see is that each regions are stratified. They are characterized by regions of high ionization closer to the ionization source, and then moving towards external regions, low ionization regions. So you need, in order to study the properties, you have to use a coherent analysis. So for the low ionization, you have to use for the temperature, for example, the N2 temperature, to measure the density using the sulfur 2 emission lines. Then moving towards the intermediate ionization, for the temperature, you can use the sulfur 3, and for the densities, for example, the chlorine 3. Then moving towards higher ionization, you can start to have the argon 4, so different emission lines, and the oxygen 3 for measuring the temperature, etc. So what we did was to measure coherently density, temperature, and iteratively using PINEB, and then calculating the metallicity starting from the density and temperature. So the first thing I want to show you is concerns the density. So for the classy systems, the density that we can calculate from the optical sulfur 2 and oxygen 2 lines that are tracing the low ionization regions are around 100 centimeters to the minus 3, more or less. If we use instead the UV diagnostics for the density, that are the carbon 3, the silicon 3, the nitrogen 4. The carbon 3, let's say it's the most prominent UV emission line that we have. It's a doublet. We measure densities that are much higher. They are 2x higher with respect to the optical low ionization regions. You can also appreciate this from the bottom panel of this figure that shows basically the difference index between the sulfur 2 densities and the UV tracers. If we go and look at the higher density tracer that we have from the optical for the low and intermediate and ionization region, you can see how they compare to the UV. And in general, there is always scatter. There is always an offset of 1 or 2x, apart from the iron 3 lines that have similar densities with respect to the UV, but still these are only upper limits because iron 3 lines are very faint and so difficult to measure. Concerning the temperatures, instead, in the UV, there is this line that is there is this oxygen line at 1666, that is a temperature tracer, similarly to the auroral line in the optical at 4363. Usually in the optical, to measure the temperature, you use the line ratio between the 4363 and the nebular emission line at 5007 angstrom. So we wanted to test if the hybrid line ratio combining the UV at 1666 angstrom and the optical line gave a consistent measure of the temperature. And we surprisingly found a very good agreement between the two, with just a small systematic offset of 1800 Kelvin that in the end basically allows to estimate the metallicity, allows to estimate the optical metallicity within a range of 0.2x, so a good estimate of the optical metallicity. And this is very good because the oxygen 3 at 1666 in our classic galaxies is 0.4x brighter than the optical auroral line, so it could be much more useful in a redshift spectra. Then concerning the ionization parameter, that is another of the properties of star-forming regions. In the optical, we have, this is again a cartoon from 2021. You have different traces in the optical that you can use, sulfur 3, sulfur 2, oxygen 3, oxygen 2, argon 4, argon 3, that basically are tracing the ionization parameter of the different ionization regions within star-forming regions. We calculated in the optical the ionization parameter using the 3 different prescriptions, finding surprisingly an offset between them. Basically, we find the scatter of ionization parameter values with so the mainly used tracer is the oxygen 3, oxygen 2. So we saw how the other two measurements were with respect to the other two, and we find that the sulfur 3, sulfur 2 ionization parameter is 0.5x lower with respect to the oxygen 3, oxygen 2, while the argon 4, argon 3 is 0.5x higher. And we interpreted this as a proof that in our galaxies we have a very high ionization structure because systems similar to redshift galaxies, and so characterized also by a very high ionization zone in the center. So basically the UV toolkit that we are providing to the community for these properties, so density, temperature, metallicity, ionization parameter is the following. Concerning UV, the densities, as I was saying before, the UV densities are 2x higher with respect to the optical densities. And we also find a slight anti-correlation between the two, with basically higher optical densities in the low ionization regions at lower UV densities. So basically, if you want to estimate the low ionization regions density for a redshift systems, that can be useful to compare with since the sulfur 2 is the tracer that we have for the majority of the galaxy, you could use this equation using the carbon 3 densities. For the temperature, you can use the hybrid line ratio between the oxygen 3 1666 and the nebular one to measure the metallicity with the direct method, finding metallicities that are within 0.2 DEX with respect to the one that you can derive in the optical. But if you don't have an auroral line, we also found a very good correlation between the optical metallicity and the carbon 3 or 3 line ratio. That probably derives from the fact that carbon to oxygen abundance is related to the oxygen to hydrogen abundance. So basically in the paper that we have recently submitted to APJ, we are providing this equation that you can use to estimate these properties. We also tested if the equivalent width of the carbon 3, that is the brightest emission line in the UV after the Lyman alpha, could be a good proxy for the metallicity, finding that there is a slight anti-correlation, but because the equivalent width of the carbon 3 is decreasing at, it's increasing at lower metallicities. But if you go to a too low metallicity, basically there is a drop in the equivalent width of the carbon 3 because the low metallicity means that at some point you don't have carbon anymore. But in general, UV diagnostics are very dependent on the ionization parameter, and you can see this from the color coding of these two figures. And for the ionization parameter, we find a good correlation using the equivalent width of the carbon 4 or the equivalent width of the oxygen 3. So in some way, this can help to break some degeneracies. Having said that, the UV, so this is basically this is part of the UV toolkit that we are creating. Of course, UV emission lines can be also used to estimate which is the main ionization source of the gas. This is part of the work in progress. This is a plot taken from Felter 2016 that shows basically the spectral energy distributions of AGN and star-forming models to explain the photo energy available, the photo energy necessary to produce some emission. If you observe the carbon 4 or the helium 2, the nitrogen 4, and so on. And in fact, in the optical, we know that there are the famous BPT diagrams that compare oxygen 3 H beta versus N2 H alpha, for example, that are very useful to divide AGN and star formation. And in fact, 2016, the first UV BPT diagram were proposed, so basically analogues to the optical diagnostics to differentiate between star formation and AGN. And then other author like Jasko Ravindran 2016 proposed the same diagrams that has carbon 3 helium 2 versus carbon 4 helium 2 to separate star formation and shocks. And then there are other works, for example, from Nakajima 2018, that propose other 3 diagnostic diagrams to separate AGN and star formation. So the classic galaxies that we have selected for our sample are all star forming. They were selected to be star forming. So basically the work in progress that we have been doing in this last month is to see how these galaxies are located in the diagnostic diagram available. In general, they are found in the regions that are dominated by photoionization, because we know that they are mainly star forming. There are some outliers that instead are very close to the AGN region, and so in this month we are trying to understand what are the conditions that move basically this galaxy into those regions in order to calibrate these diagnostics. And the last thing that I wanted to say is that like among the future perspective, among the future works that we have been doing, that we will do, last year I submitted an HST proposal in cycle 29 that was approved, and this is to do imaging of UV emission lines, basically for 3 galaxies of our system that are characterized by three different Lyman alpha profiles, but characterized by carbon-4 emission, helium-2, oxygen-3, and carbon-3 with different line ratios. Basically, we'll do imaging of these UV emission lines in order to investigate the distribution of UV properties. Since in the UV we don't have integral spectroscopy instruments at the moment. And this would allow to do the first UV BPT map spatially resolved. And also we are collecting using recently we got other observations for other 9 galaxies of class C using KCWI at Keck in Hawaii to get the intergalactic spectroscopy in the optical to study how the properties of the ISM vary in the optical for these galaxies. But this is all work in progress. So here I leave you with my conclusion. I hope that I convinced you that rest-UV spectra are rich in diagnostics, are very important, especially in the JWST era, but we need to properly calibrate them before. If you want to know more about the class C, there is a web page where you can find all the information, and there is also a mass portal where you can download the spectra. And there are also Jupyter notebooks in order to deal with the spectra, etc. And thank you for your attention.
Thank you, Matilde. So, do you have questions?
Yes.
Please go ahead.
So the first one is regarding the results of the 2 decks higher density, and also with the radiation field. There was a disagreement between optical and UV lines. I didn't understand properly which is the interpretation. So what are they tracing different regions?
I think at the beginning I didn't expect this clear offset, but then I understood that basically the carbon-3 in general, the carbon-3 lines are tracing intermediate ionization regions. So they are coming from. These intermediate regions, so slightly higher ionization region with respect to the sulfur 2. And then also it depends on the critical density that these ions have, and the carbon-3 critical density is higher with respect to the sulfur 2, for example. A thing that we didn't expect was the offset with respect to, for example, the argon-4 densities, because the argon-4 densities are tracing the very high ionization regions. And so we would have expected like that the density structure was more or less following the ionization structure, but apparently it's not like this. No.
You are still finding an interpretation of this?
So the interpretation, so there could be 2 things. In the UV we have the nitrogen 4 doublet. We have this doublet only for 2 galaxies, unfortunately, because the lines are very faint, and these are tracing in theory regions that have the same ionization of the argon-4 lines. So, but still there is an offset of 1 dex between the 2. So it could be that still they are not tracing exactly the same regions, and so the nitrogen 4 are tracing denser regions, or it could be that we are using PyNeb to calculate the densities and the temperature, and PyNeb has some atomic data, and the argon-4 is very dependent on the atomic data that you are considering, and using different atomic data you could get slightly different values of the properties.
So it depends on the code.
Because, for example, the densities that you can estimate with cloudy for the argon-4 are 1 dex higher, so there could be also that offset to take into account. But in general, the important thing is to, like, carbon-3 densities are 2 dex higher with respect to the sulfur 2, so that could be already a good way to estimate one from the other, basically.
The other question is, how do you consider the dust extinction on the UV lines? Because it is differential, so
yeah, that is a problem. So what we did was, I said before that we iteratively calculated the density and the temperature. Actually, we calculated iteratively also the dust extinction. What we did was we used the different attenuation curves. In the optical, we are considering a Cardelli because we found that for our systems it is representative for the optical attenuation. And but in the optical, it doesn't matter too much in the optical wavelength range. In the UV, of course, it's a problem. The different extinction curves are very different slopes, etc. And we are using REDBY 2016 because up to now it's the only one that is calibrated on real data. So we're using two different attenuation curves, but we are using the Balmer decrement to correct for the dust extinction. In the UV, using the stellar continuum. Fitting the stellar continuum, you can have the beta slope. So the slope of the stellar continuum can tell you the measurement of the stellar extinction. And so we compared that with the Balmer decrement. This is also part of this work, but I didn't put this in presentation because it was too long. And we find an agreement between the two, between the B minus V of the stars and of the gas at very high specific star formation rate at very high specific star formation rate. So we find that they are similar, but yeah, of course it's a problem, the dust extinction. It
cannot affect these results.
No, because the carbon 3 lines are very close one to the other, so you don't need to correct them for the dust extinction. They are very close. One is at 1907, the other at 9. So there is a difference of 2 angstrom. It can of course affect the temperature tracer, because if you have one line in the UV and one in the optical, you have a very there is that, but that is considered basically in the error bars of the line fluxes.
Yes. Thank you so much. So have you guys checked if there's any archival IRS data of these sources, since they're mainly nearby, right? These are all local dwarfs, right? And so in the mid-infrared, you can, kind of adding on to this question of properly accounting for obscuration, be doing direct comparisons with something that's less effective, and also have an additional comparison of these diagnostic parameters, but with mid-infrared diagnostic parameters. And so I'd be curious to see if that would help at all.
Actually, no, I'm not an expert about the mid-infrared. I don't know. I didn't look into that. For sure, it's a thing to do. Like at some point, we should start to collect data, multi-wavelength data covering all the properties. So the answer is I don't know. I think that there are WISE data. I don't know if it's the same wavelength range that you are.
Well, with the IRS spectroscopy, you could look at a variety of atomic species, but also I think depending on what you get in the optical, you might also get some of the same species within the mid-infrared.
Maybe we can talk later, because I want to ask you some questions about this.
I think somebody of the collaboration looked into this like a couple of years ago because we submitted a JWST proposal by then. So I think we couldn't really take much of the IRS information by then.
Yeah, I have to look into that.
We submitted a proposal to get the mid-infrared argon, for example. It didn't get us exactly. It didn't get a code. So
yeah, I will look into that again before next January. When there is the next deadline for JWST.
No, I told you.
If there are other questions. For the people connected remotely, do you have other questions? So, if there are no other questions, we thank Matilde.
Thank you very much.
Thank you.